I'm blaming this on Tom Ross, and I will go on record to say that he's the worst of all the Rosses. I don't mean that. Okay, in a display of solidarity to the unionization of Santa's elves, you have devised that you can melt the ice and heat the water of an icy world planet by kinetic bombardment. This will allow kinetic energy to be transferred to needed heat energy. Assume that there is some mass of ice in kilograms. So that's not the word mice there. That's the mass of ice in some kilograms at temperature T ice. So the ice is at a temperature. And it's resting in some mass of an ocean with some mass. Given the nearby stellar composition, we can assume that the core of this planet is a uniform iron core that is 1.2 times 10 to the 6 meters in radius, and it's at a temperature of that of the ocean. Yeah, I know that's like weird, but it's all at the same temperature. It makes our problem slightly easier. If the asteroid we plan on dropping on this planet, for the kinetic bombardment, has a mass of mass asteroid, and the atmosphere in a rough calculation is going to reduce the asteroid's velocity by 20%, what we need to do is to set up an analytical equation for the planetary scan team so that when they arrive and find the values of the planet, they can quickly release the asteroid from a known distance from the center of the planet and raise that planet's temperature to 310 Kelvin. Assume that due to the magic of the elves, that the heat is generated uniformly and is distributed over all the contents of the planet. So we don't have to worry that, the iron core is in the middle of the planet and there's going to be some heat transfer due to Newton's law. It all cools uniformly at the same time. Otherwise, this becomes very difficult for a whole slew of reasons, okay? And we're doing this analytically, so we don't care about numbers. Although there are a few numbers that we can assume to be the case here. In this problem, this is really just a long calorimetry problem here, with a few things going on that we can recognize. First, there is some ice here, okay? We have ice, we have an ocean of water, and we have an iron core. These are the main three things that we have. And they're going to be heated up due to the asteroid. Now, when we think about calorimetry, if we start with ice, we normally have to think of the fact that we may have to heat the ice up so it gets to 0 degrees Celsius, and then we could melt the ice. But this isn't true in this specific case. I can ignore the energy needed to heat the ice up because this ice is floating in water. This implies that since there is some liquid water here with ice in it, that the temperature of the ice is already at 0 degrees Celsius. If that ice was less than that, that would imply that all the water has frozen, which isn't the case. So we don't have to heat the ice up. What we will have to do is we are going to have to melt the ice. We are then going to have to heat the melted ice, because now it's water, right? We got to heat that new water up. We have to heat the ocean, and we have to heat the iron core. Now, one of the questions that could arise is, well, what if this asteroid is dropped in such a way that it vaporizes the ocean, or it even vaporizes the iron core? We'd have to then change a phase state for those and then heat up that steam or that vaporous iron. But we don't have to worry about that. We are just trying to heat this planet to 310 Kelvin. That is not hot enough to bring our water or the iron up to a vaporization point. So we don't care. And remember, due to the magic of the elves, we don't care about localized effects like vaporizing specific parts of this planet and killing all the elves. we're saying all the energy is magically distributed evenly. So all we have to say here then is this is going to be some mass of the ice and a latent heat of fusion, because we're trying to melt that ice. We then add that to an mc delta T, where this is the mass of the ice that we just melted. This is the C of water, because that ice has now turned into water because we melted it down. And then there's some delta T here. Now the great thing about this delta T is we already know what it's going to be. It's going to be our equilibrium, which is 310. Let's just call it TEQ, but it will be 310. Minus the initial. And we know that since this started in ice water, this water's at 0 degrees Celsius. So this is TEQ minus 0. So we can just close it. Then we can add the mass of the ocean times the specific heat of the H2O multiplied by TEQ again, because that's going to be TEQ minus 0 because the ocean was at frozen temperatures. And then we do the same thing for the iron. It will be the mass of the iron, which I will subscript with an Fe because that is iron, ferrous. There is some specific heat of iron, which nobody knows off the top of their head. And then we're going to have some TEQ here as well. That's that 310. And we are just going to assume that the iron core of the planet is also at 0 degrees Celsius. Now, something a little tricky here is we don't exactly know the mass of the iron. We just know the radius of that iron core, which does indeed mean that if you actually want to put this in full analyticals for the planetary scan team, in order to get that mass, you would have to remember that density equals mass over volume. So you could say that the mass equals the density of the iron multiplied by the volume that iron occupies. And since that iron core is in a sphere, you could say that this was equal to 4/3 pi, the radius of the core, cubed. And you would take this quantity and move it up into the mass, if you just wanted to take this a little bit further. Once we have all that, this is going to be equal to the kinetic energy from the asteroid, because that kinetic energy from the asteroid is what is causing this heat. So this has to be equal to a 1/2 m of the asteroid multiplied by the velocity of the asteroid squared. This also means that if you wanted to find or solve the velocity of the asteroid, we would multiply by 2, divide by the mass of the asteroid, and then square root everything. So we get this kind of funny equation. We would take this entire quantity, multiply by 2, divide the whole quantity by the mass of the asteroid, and then, icing on the cake, we need to take the square root of everything. And when I mean everything, I mean everything. And that would give us the velocity of the asteroid. But we're not done there. Remember, the atmosphere, on a rough calculation, took off 20% of our asteroid's velocity. So, while this is the velocity of the asteroid at impact, that's not the velocity, or that's not going to help in terms of the distance away we need to drop things at. What we need to do then is we need to say that this velocity of the asteroid needs to be increased by 20%. So what we really want here is we want to take the value of 1.2 times the velocity of this asteroid, and that will give us the actual velocity that we want. That's the actual velocity we need when this object is going to strike the atmosphere. Now the question becomes, if this is the actual velocity we need, let's give this a value. Let's call this like V real, okay? This corresponds to some amount of kinetic energy, which means that the kinetic energy would be 1/2 the mass of the asteroid multiplied by V real squared. Now, to get this kinetic energy, we need to drop this asteroid from a specific position, which means that we need to drop this asteroid thinking about things from a gravitational potential energy. And we can think about this then with the gravitational potential energy as G multiplied by the mass of the planet, which we'll have to talk about that in a second, multiplied by the mass of the asteroid divided by R, where R is the radial distance that we are from the center of this planet. That's the location we're going to be dropping at. Now, while the mass of the asteroid is just the mass of the asteroid here, the mass of the planet is a little bit up to debate. If we only say the planet is made up of ice, water, and an iron core, then technically the mass of the planet would then become the mass of the ice plus the mass of the ocean plus the mass of the iron core. And this can be solved for. To solve for R, we'll bring the R over, we'll bring the 1/2 mv squared all down underneath. What we get here is that R equals G, and this problem is getting big, so my computer's having a hard time writing. It's going to be G times the mass of the planet, which was really the mass of the ice plus the mass of the ocean plus the mass of the iron core times the mass of the asteroid divided by 1/2 the mass of the asteroid, which is nice because now our asteroid masses are going to go away here and it doesn't matter. Although it really should, thinking about it. And then this will be our V real squared. And we knew that V real is 1.2 multiplied by our V asteroid, which is this giant term right here. This giant thing, that square root of 2 times the entire... I don't even want to write that out, but that's what we would have to write out right there. And I guess the really cool part is because we're squaring this, the square root goes away. So this will just be 1.2 times the quantity of 2 multiplied by that entire calorimeter equation. Right? Like this is the, like everything that goes in there. And then that was divided by the mass of the asteroid. And then since that square root was there, but we... Oh, you know what? We actually, I stand corrected. We do need to throw the square root on this thing because this square is also taking part on the 1.2. But the nice thing about this is because this mass of the asteroid is in the denominator of the denominator, it will pop up top, which implies that larger asteroids will help us out a little bit more. And that should be the final solution to this problem, assuming I didn't make an error somewhere. This problem's a pain because it's so analytical and I don't have any real numbers there. And it's kind of like a little bit made up in that regard of everything is uniformly mixed. But that is the idea that's going on. So with that, this problem, given originally to Miss Allison Spadero, is finished. Until next time, adios, and take it easy.